Lecture number 4, moment inertia of a solid. We have three questions, and the first question, moment of inertia, and the second question, proof of the parallel axis theorem, and the question number 3, rotational kinetical energy. And here, the first we know, and or if rigid body in the continuous distribution of mass like of this solid cylinder or the solid sphere. And it cannot be represented by a few points methods. It is this case of the sum of masses at the distance that define as the moment of inertia. We know, and here this is figure and show and axis of rotation in here. This is axis of rotation, three mass, and one and the first mass M1, M2, M3, and we have and the 3 point, and we using of the material point. We know of the moment inertia of the material point and r square. R is the distance between two points and maybe two particles of the mass M1, M2. But and here this is a formula of moment inertia of the systems, and the systems continue three, and here this is systems consists three mass and M1, M2, M3, and this is distance between of the mass and first mass and second and third, and first and third, and this distance between and two particles other. And moment inertia we know of the system international unit of moment inertia in the called and kilogram multiplied by square meter. This is moment inertia, the unit of moment inertia. And moment inertia, moment of inertia and rotational kinetical energy. In here, this is the moment inertia of I, the notation J, and of a body about given as the axis is a measure of its rotational omega, and here. And the greater the value moment inertia, the more difficult it is to change the state of a body of the rotation. We know, and when the one body maybe or disc or sphere or cylinder, etc., and then that and moment inertia and can be the difference of the body, and the moment inertia can be expressed as a sum over the particles make up of the body, each which in the one perpendicular distance from the axis, and the rotational kinetical energy of rigid body rotating about fixed axis of dependence and angular speed and the moment inertia for that rotation. And here this is we see and moment inertia of uniform bodies, various shapes, and in here the cylindrical shell about axis, and this is a cylindrical shell and with the radius r cylindrical shell, and moment inertia of the cylindrical shell equal m mass of the cylinder and multiplied by square radius. And we take a solid cylinder about axis. Solid cylinder maybe we using on the task disk, we using a moment inertia of solid cylinder too. And here this is axis. And this solid cylinder with the radius r, and moment inertia of the solid cylinder will be mr squared divided by 2, because this is solid cylinder. When and cylindrical shell we're using an mr squared. Hollow cylinder about axis, and here this is length of the cylinder, and moment inertia. Okay, and here this is hollow cylinder about axis, and L, and here And here the using and two radius, and the radius R1 and 2, and moment initial and total moment initial will be and 1 divided by 2 multiplied by m, and the sum of the square radius 1 and plus radius 2, square radius 2. And when in the cylindrical shell about diameter through center, maybe and axis, and through center of the diameter, and about the diameter through center in here, this is length of cylindrical shell and this is radius. We'll be using formula of the moment initial 1 and here we know, and cylindrical shell moment initial moment initial 1 divided by mr square and plus moment initial because and axis is through center moment initial 1 divided by 12 ml square. M, this is mass of the cylindrical shell, and L, this is length of the cylindrical shell. And solid cylinder about diameter through center because and using and solid cylinder about diameter through center in here, and moment initial will be and 1 divided by 2 for mr square and plus 1 divided by 12 because and axis is through center on the diameter in here. And we're using moment initial 1 divided by 12 ml square in here. And when and using on the task maybe thin root about and here we're using the thin root and axis through center and the thin root perpendicular line through center in here. This is line of thin root, length of the root. And we know and moment initial when moment initial of the root when a perpendicular line through center using formula 1 divided by 12 ml square. When and then root about perpendicular line through one end, we're using formula moment initial 1 divided by 3 ml square. Maybe as the task we using on that sphere and then spherical shell about diameter. Then for then spherical shell about the diameter formula of the moment initial 2 divided by 3 mr square. R, this is radius sphere. When and the example for example our solid sphere about the diameter and solid sphere about the diameter moment initial 2 divided by 5 mr square. But and example and solid rectangular parallelepiped about axis through center axis, and here this is axis through center perpendicular to the face in here, one face and through center and the second face. And solid say moment initial of for solid state rectangular parallelepiped, and here in here 1 divided by 12 m, and here this is two side and a and b, a square plus b square. Okay, and the second question, proof of the parallel axis theorem. We in here we know, and when we know of the different moment initial for the different shape, we know moment initial of the cylinder, we know moment initial of the thin root on spherical shell, etc. But when and we should to calculate it the moment initial of moment of initial. And the parallel axis theorem. We know, and the parallel axis theorem relates the moment initial of a rigid body. We're using in here, this is this configuration. We and a rigid body of mass m in here, mass m. This is rigid body of mass m. About two parallel two parallel axes. In here, this is one parallel axis through center. The second parallel axis and a distance from a distance d in here from the first axis, and in here this is distance d. If the body has a continuous mass distribution, if body has continuous mass distribution, the moment inertia can be calculated by integration. If we using formula of parallel axis theorem, and here this is moment inertia of the one end is the body, the rigid body, and here we're using moment inertia of the center mass in here plus mass of the rigid body multiplied by distance between and here between and point P and the center mass. And here this is proof of the parallel axis theorem, because and here this is two moment inertia, one moment inertia of the center mass, and here this is m d square, this is moment inertia one end of the rigid body. We now the velocity of the center mass, relative to any point on the axis of the rotation. We know formula velocity of the center mass h multiplied by omega. And here we know of the kinetic energy of the motion of the center mass. We know, and in here this is a kinetic energy mv squared divided by 2. And here we using of the center mass. This is a notation of the velocity, velocity of the center mass. Okay, mass of the in here. This is mass of the rigid body m using. Okay, and here we know and the velocity of the center mass are relative to any point of the axis of rotation. And here we're using here formula, replace and put on the formula in here h omega. In here this is omega square, eh square in here. E will be the relative energy we know, and E omega square divided by 2. In here this is formula. This is formula kinetic energy of the motion of the center mass, and using of the kinetical energy equal in here kinetical energy of the motion put in here. This is formula E n plus relative energy. E and final formula in here I put in here. This is 1 divided by 2. I put on the bracket. E and open the bracket mh square and omega square 2. E and mh square plus moment inertia center mass. E and in here this is we know this is moment inertia, because in here this is in here this is rigid body. We know moment inertia center mass plus md square, and to replace in here this is moment inertia in final formula of in here E omega square and 2, because we know and this is and parallel axis theorem, and we know the kinetic energy of a rotating object is the sum of kinetic energy individual particles in the object, because and this is system rotational this system, because one body and consists particle and the kinetic energy of the mass element of the rigid body. In here this is formula kinetical energy of the mass element. But and here the all element using of the all element and linear velocity radius multiplied by angular angular velocity. And here, this is put on the K kinetic energy, rotational kinetic energy, using formula in here, the sum, and replace and V and R omega replace, and R omega square, and final formula in here, mr square divided by 2. This is moment inertia of the system particles. And here the formula, this is formula, and final formula, rotational kinetical energy of rotation. But in the compare, we know of the kinetical energy of the motion and kinetical energy of rotation. In here, this is kinetical energy for linear motion. And for of the rotation, and here this is formula we're using. In here, this is mass for linear motion, and this is moment inertia, because the system particle and rotation rotational on the axis, and okay, and this is this is table analogs and rotational and linear motion, and this is column in here, one column, and rotational motion in here. This is linear motion, we know, and analogies, angular displacement delta theta. Okay, linear motion delta x. And here, this is angular displacement. Angular velocity, we know. Angular velocity is the first derived angle of the time. We know of linear analogies and linear velocity, instantaneous velocity. Instantaneous velocity is the first derived position of the time. But angular acceleration, we know formula. Angular acceleration in here, the first derived angular velocity, but maybe the second derived angle of the time. We know acceleration, this is characteristics of the motion. And the first derived of the velocity, the second derived of the position. And here, constant angular acceleration equation. We're using of different constant angular acceleration equation. In here, this is. This is constant acceleration equation. Constant acceleration. And here, this is. And here, theta equal theta 0 initial angle plus omega 0 t and plus 1 divided by t. Angular acceleration t square, and following analogies and linear motion in here, this is x equal x0 plus v0 t plus 1 divided by 2 at square in here. Torque and tau, force and F in here. Moment inertia in here, this is mass. Work, we know formula of the elementary work, and here this is elementary work for rotational motion. Power, we know formula, angular momentum, and Newton's second law. We know Newton's second law in here, this is linear motion, and the linear motion and MA, and maybe in the second formula, and the first derived momentum of the time in here, and Newton's second law, and the first derived and angular momentum of the time. This is analogy. This is table analogies in rotational and linear motion. And today we studied moment inertia and the different moment inertia for different shape, and we studied kinetic energy, rotational kinetic energy, and final in here. This is proof of the parallel axis theorem. Proof of the parallel axis theorem too. And compare in here rotational motion and linear motion. Thank you for attention.